12 volts, baby. It's alive. And that's 5 volts, baby. It's hard to see. I can't put the light on because it washes out the LEDs. But I've got the entire power supply circuit soldered in now. The inductor, the LEDs, the filtering capacitors, and the 5-volt regulator. And we're making 5 volts, which I tested right there at my 5-volt test point. All right, let's keep going. Okay, folks, here we have it. The final assembled board. Sorry for a bit of glare, but here she is, looking good. We've got the power supply and input connector in this area. We've got the CANBus in this area. We have the USB in this area, and I'll talk about that in a minute. Reset button, debug header, power supply filtering for the microcontroller, the current sensor itself, and the input and output pins. And minimal work on the bottom except for soldering the crap out of these guys to make sure that we've got enough current handling capacity. Okay, we're wired up. Now, given my luck with the rest of my electronics projects, the only thing I'm looking for here is for these LEDs to light up and no smoke. I'd be happy. There's no firmware loaded in this. There's no power flowing through it. Nothing should happen. So, here we go. Oh, okay. We have good power supply. And I don't know if you can see by the glare. Let me use something non-conducting. This LED is lit up. The CANBus receive light is on. Let me turn that away. You can see right here, CANBus receive, focus. Now that's a function of the CANBus chip, but the microcontroller shouldn't be sending it any data, so I don't know why that's on. And the receive, oh no, sorry, that's the receive. The transmit light is on but very dim. The receive light is on full blast. So I wonder if it's just, maybe it's just polling the bus and it's waiting for traffic because I haven't loaded any software in yet. Well, that's good. Now, let me walk you through my lessons learned with this project. The online parts catalogs are great, but don't put your complete trust in them. Trust but verify, as Ronnie used to say. Compare the layout with your physical part before committing to the design. Unfortunately, I was doing board layout while the parts were still on their 2-week trip from China, so I thought I could optimize the timing. Nope. I have 2 big problems. The package for the current sensor chip did not have the big tab slot cut in it. Whether that has to do with the part layout, the generated Gerber file, or the peculiarities of the PC board company trying to mill that slot, I don't know. All I know is that there's no slot cut right here. I drilled enough of the slot to get the part in place and soldered the crap out of it to close up any gaps. The package for the USB driver chip is wrong. The chip specs call it a 20-pin QFN package that looks like this, but the parts catalog has pins like this. This all means that the pins don't line up no matter what I do on the board, and this will require an update to the package and how the pins are wired, and a new revision of the circuit board. The bottom line, this could be fatal for the version 1 board layout because I need the USB to do 3 things for me. Load my firmware, debug the code, and provide a way for the end user to adjust the CANBus ID and the calibration values. Now, I may be able to avoid number 1 and number 2 with the use of the Atmel debug header, which I cleverly placed into the design, but I don't know. The Atmel tool is very expensive, and I'm lucky I had one because I planned to use it for the JevQ firmware debugging at least a year ago. I bought generic push buttons for the reset button and took an educated guess at the pin placement and wiring and made my own pattern. Both were slightly off, but I can easily adjust that in the design, and I was able to cut some traces and get the push button installed on the board with full functionality. Oh my Buddha, every part in this thing is really, really, really small. Try soldering half a grain of rice, like the size of some of these resistors. You'll get the idea. I, for one, welcome our robotic surface mount technology assembly overlords. But seriously, the tiny chisel end of my programmable soldering iron really works the best for all of the parts in the design. You get a good technique after a while. I'd put a tiny amount of solder onto one pad, hold the part in place with the tweezers, and then heat up that pad to get it tacked down. Then I would properly solder the other pads, and then come back and properly solder the first pad again. I bought 2 conductive plastic tweezers which were sold in the soldering iron section of the store, but upon first use, the tip melted. So I switched to drugstore tweezers, which work really, really well, but don't touch the tip for a few seconds after you take the hot air gun or the soldering iron away. Use very fine solder for assembly for the parts in this design. This one is 0.4 millimeters thick. This is 1.2 millimeters thick. This one is far better for surface mount technology soldering. This syringe solder flux works really well for good solder joints, nice and clean and shiny joints. I learned about this from Louis Rossmann. Check out his YouTube video. He uses this stuff all the time when he's repairing Apple circuit boards. Something produces a sticky goo when I'm trying to clean the board, either the residue of this flux or in conjunction with this cleaning solvent, which I use with this little tap dispenser bottle. The man at the store said this was circuit board cleaner, but if you'll see, it's got hazard statements and precautionary statements, and other than calling it cleaning solvent number 2, it doesn't say what it does. Please, if you're selling toxic chemicals, put something on the label to tell people what it does. That's all I ask. When it made this goo, it was really hard to clean off the circuit board. So I'm going to try and find a new solution for this. The hot air gun is not good for assembly, but it's absolutely required when you're desoldering both simple and multi-pin packages like the 20-pin USB chip that I was faffing around with. You'd never maintain enough heat on every pin to get that off with just a soldering iron. And this also does not like to be run off my uninterruptible power supply because it just beeps at me. I need a better solution for light and magnification. I have this headband magnifier that keeps falling down like in Monty Python and the Holy Grail.
We have found the witch, may we burn her?
Paired with this articulated desk lamp. But I was always moving the lamp around to get the best light, and my head kept getting in the way. And when I needed to get a very close view, I would put another lens in front. And so that's just not workable. So a lighted bench microscope would be best, but I've ordered this 10 times magnifying lens light from China, and I'll try it out when it arrives. I bought this adjustable circuit board holder in preparation for the project, and it's perfect. It adjusts this way, it tilts, and it's spring-loaded, so it keeps the board nice and tight, and it sits on the table really well. So I highly recommend this. I bought several packs of assorted SMT resistors and capacitors on AliExpress. They're dirt cheap, and it's worked out really well. It's always good to have a lot of these on hand, and they come in these robotic dispenser reels, which is cool. The resistors are marked with a special code, and the caps are only marked on the paper that holds them. So You have to find a good website with tables of codes so you convert from the code to the component's actual value for use on your board. Another thing to consider, as I was waiting for the boards to come back from China, I had a thought. Why don't I add voltage measuring functionality to the board too, so it measures both voltage and current of the same circuit? That way you can calculate power, and that makes a good independent device that you can stick in nearly any project, and you get the two most important factors for the wire that you're interested in. So I have to look at the way I would need to read voltage into the microcontroller, and if I have to do a voltage division kind of a thing, because it can only read up to 3.3 volts or 5 volts, so I would have to scale it down. I'd have to condition it to make sure it didn't destroy the microcontroller, and there's some other factors that come into play. I need to think about accepting 5 volts from the USB cable. This is useful during firmware development and when the end user is setting up the CANBus ID and calibration factors. You shouldn't need 12 volts just to prep the board, but you will need it when it's installed in your vehicle. Maybe I could use jumpers or cutting a trace on the board to switch between 5 volts from the USB and 12 volts from the connector, but it's something to look into. Overall, it's definitely been a fun project. Getting to bring your design to life is very cool. Don't get discouraged, because there's always going to be a version 2, and there may be a version 3 and a version 4. Just enjoy it and have fun.
As you stare out on my beach, I would ask you to subscribe to my channel and click like on this video so YouTube thinks I'm worthy again, and I have so many people on my channel that they'll give me 10 cents a day in ad revenue. So I thank you for that.